Okay, so now we're going to go on to 6.5, which is drawing the reciprocal trigonometric functions. So far we have looked at the primary ratios, which are sine, cosine, and tangent. Now we're getting to the reciprocal, which are secant, cosecant, and cotangent. We're going to start with the reciprocal of the sine theta function, which is the cosecant theta function. And in order to graph this, we're going to go back to what we learned about drawing rational functions, or originally when we looked at how to graph reciprocal functions. And there were 3 steps, right? 3 steps. The first one is wherever your graph crosses the x-axis, wherever there's an x-intercept, there's an asymptote for the reciprocal. Wherever your original function meets y equals 1 or y equals -1, your reciprocal will also go through that point. And wherever your original function is increasing, your reciprocal will decrease. And whenever your original function is decreasing, the reciprocal will be increasing. So let's put all those into practice here. The first step is at my x-axis, I will have vertical asymptotes. And so every x-intercept gets a vertical asymptote. Then I'm going to identify where y is equal to 1 and -1. Okay. Now, this function, as I go left to right, it is increasing, so my function will be decreasing going towards the asymptote. This function is increasing from the asymptote, my function will decrease from the asymptote, right? And then it decreases, so mine will increase, decreasing, and then increasing, so our reciprocal function will increase and then decrease, increasing, so my reciprocal will be decreasing. So you can see that it is essentially a set of alternating parabolas. Up, down, starting, and then the asymptotes would be 0, pi, 2 pi. At every pi intervals, there is an asymptote. There are parabolas that you can see in between the asymptotes go through y equals 1. So in essence, the max and mins of the original function are being used as the local max and min of the parabolas, or the parabolas that have been formed in that group. So that is the sine theta to cosecant theta. Let's apply the same concept to cosine and the secant theta functions. So now we have our cos theta function. In order to graph the reciprocal, which we'll label as g at x is equal to secant theta, first we start with our asymptotes. Wherever our original function passes through the x-axis, the reciprocal function has a vertical asymptote. Then wherever the original function passes through 1 and -1, the reciprocal will have at the same point. We'll share that point, because wherever the original passes through 1, the reciprocal will also pass through 1, and the same goes for -1. Finally, as my function is increasing, the reciprocal will be decreasing. So we have increasing to decreasing, so my function will follow the same pattern, decreasing to increasing in its reciprocal nature. This function is decreasing and then increasing, so the reciprocal will increase and then decrease. Increasing to decreasing will result in decreasing to increasing, and then it would just continue in that pattern. So you can see that the function is identical to the cosecant theta function. Just like the sine and cosine are the exact same function, exact same graph, just shifted to the left or to the right by a little bit, depending on how you're looking at it. The secant theta and the cosecant theta function are also the same graph, just shifted to the right or left by a little bit. In the secant theta function, your asymptotes start at pi over 2, and then you can go to the left or to the right by an interval of pi to find the next asymptote. For the cosecant theta function, the original asymptote was at 0, and then you can go left or right by pi to find the consequent asymptotes. The final one we're going to look at is the cotangent theta function, and for that we're going to go back to how tan theta was created in the first place, or how we came up with a graph for the tan theta function. Okay, going back to tan theta being sine theta over cos theta, what we knew is that wherever sine theta is equal to 0, we would have our x-intercepts. So we have an x-intercept at 0, at pi, and at 2 pi. And then wherever cos theta was equal to 0, we'd have our vertical asymptote. So cos theta has zeros at pi over 2, and then with every in every interval of pi, you would have other ones. Then that's how we got our x-intercepts and our asymptotes. The rest of it was understanding the pattern. From 0 to pi over 2 is quadrant 1. So our function in tan in quadrant 1 is positive. And over here is negative. From pi over 2 till pi is technically quadrant 2, in which we know tan theta is negative. Quadrant 3, tan theta is positive. Quadrant 4, tan theta is negative, and then 2 pi to 5 pi over 2, 5 pi over is going to be back to quadrant 1 again, which is positive. So we end up with this function simply by following what we know about using what we know about rational functions. Sine theta, the numerator set equal to 0 gives you the x-intercept. The denominator equal to 0 gives you the location of the vertical asymptotes. And then we look at the cast program or the cast idea to know that from 0 to pi over 2 in quadrant 1, tan is positive, negative, positive, negative, positive, and it continues on in that pattern. Let's apply the same concept to cotangent of theta. Cotangent theta is the reciprocal of tan, therefore it would be cosine theta over sine theta. First step, cosine theta, wherever the numerator is equal to 0, we would have our x-intercept. So they would be here, here, here. Basically, the asymptotes of tan theta now become the x-intercepts of cotangent theta. And wherever the denominator is equal to 0, so wherever sine theta is equal to 0, that's where we're going to get our asymptotes, which means the zeros of the tan function become the asymptotes of the cotangent theta function. And now we apply the same thing. So now we have an x-intercept here and an asymptote here, and we know that it should be positive. So it will follow this pattern now, right? Applying the same same rules that we know about cotangent theta and which quadrants it will be positive in, right? It would continue on in this method. So the green function, again, what we've done is switched the asymptotes and the x-intercept for between the tan and the cotangent theta function, and which results in the graph actually flipping. Instead of going up and to the right, now the cotangent theta function comes down and to the right. Again, this is more of an exploratory section where we're just trying to understand what the graphs would look like. It's important that you are able to produce these graphs on your own. The reciprocal functions are quite a bit easier to graph than the original sine theta, cos theta functions, because all you really need to know is where your asymptotes are, and in the middle of each of those asymptotes would be your parabolas opening up and down for the cosecant and secant theta functions. And for cotangent, you're just trying to understand what is your period, 1, and 2, what is where's the location of your asymptotes and x-intercept, because after that point it's the same thing. So if your asymptotes are pi and 2 pi, that means in the middle will be your x-intercept, and the function's original form will be as given here.